In this lesson, we will study some properties of conductors in static situation. Static here means all the charges are at rest, none are moving. For a conductor in a static situation, net charges can only be found on the surface. Let's say this is a piece of conductor and it carries a net negative charge. Since a conductor allows the charges to flow, that means the negative charges, they're going to repel each other, so they get as far away from each other as they can, and they move onto the surface. And the electric field is zero everywhere inside the conductor. Now let's just say, suppose the electric field over here is not zero. There's an electric field going that way. Even though this region inside does not have any net charges, but we still have equal number of protons and electrons in this region. So we still have free electrons right over here. If we look at a free electron right here, there will be an electric force going the opposite direction to the electric field acting on the electron. And because this electron is free, this force will push that free electron that way. If the free electron moves, that means that we no longer have a static situation. So if it is a static situation, the electric field has to be zero inside everywhere. But since there is a net negative charge, there has to be electric field lines going into these negative charges. Those field lines are all outside the conductor, and the electric field has to be perpendicular to the surface immediately outside the surface. The lines can bend, but immediately outside, the field lines have to be perpendicular to the surface. Let's see what happens if the electric field is not perpendicular to the surface immediately outside. Let's say we have an electric field going this way. This electric field would have two components. One component that is perpendicular to the surface. The other component will go like this, that way, parallel to the surface. For a free electron at the surface, this perpendicular component of the electric field would cause a force in the opposite direction to act on the electron, which pins the electron against the wall. And that is okay because it is not going to cause the electron to move. However, this parallel component of the electric field is going to cause a force on the electron going that way. Since the electron is free to move, it gets pushed by this electric force, so it will move along the surface. If the electron is moving, that means it is no longer a static situation. So if it's a static situation, no charges are moving, there cannot be any parallel component of the electric field over here. The electric potential is the same everywhere. Let's see. The electric field lines are perpendicular to the surface. If this surface is perpendicular to the electric field, that means this is an equal potential surface, which means the electric potential must be the same everywhere on the surface of this conductor. And we know that if we follow the field lines, the potential would decrease. Since there is no electric field inside the conductor, there are no electric field lines inside. So the potential does not change when we move from the surface to the inside. Therefore, the electric potential is the same everywhere, on the surface and inside of the conductor.